I would like to acknowledge the aquarium, though. Monterey Bay Aquarium was founded by the late David Packard of Hewlett-Packard, and our mission statement is more or less better instruments, systems, and methods for exploring the ocean. I'm going to talk to you today about really an application of much of the work that we've done to develop sensors, biogeochemical sensors that are deployed on Argo. Argo floats. So 2 points before I start to talk. Also, much of this work, 3 points, supported by the National Science Foundation, Polar Programs, NOAA, and NASA. I want to acknowledge them. Giving this talk before the talk by Argo is a bit like a teenager who just got his driver's license, now lecturing the parents on safe driving. Okay, so I just want to make a point that Argo is really, has done tremendous things, and I'm going to really want to build in that platform. Might have been more appropriate for Toshio to give his talk first, but anyway. And the third thing I want to say here is that I have been encouraged to speak a little bit more broadly than just about applications to profiling floats. I'm going to kind of ignore that request to some extent, but every time I say profiling floats, you should think gliders, ocean moorings, other sensors, because the things that I'm going to talk about today have a very broad set of applications in the ocean sciences. So to get right into it, so prospects and rationale for a global biogeochemical Argo system, BGC Argo. But again, I want to acknowledge, before I go very far, the tremendous work that has been done with the Argo system. And I think there was a comment earlier that Argo is in the GCOS implementation plan. It was a success story. These two papers really summarize much of the great work, the 15 years of Argo and the unabated planetary warming in its ocean structures since 2006. You might see that later. But Argo has been really key to our understanding of how the ocean is warming. Much of the warming has occurred in the Southern Ocean as opposed to other areas of the ocean. Phenomenal results. And really, Argo has transformed global-scale oceanography into global oceanography. This is a map. Color scale is the number of profiles per 1 degree square that reach 1,000 meters for the Argo program, and this is the same kind of a plot, the number of temperature and salinity profiles that reach 1,000 meters based on ships. And on the ships, you see broad areas where there are no temperature salinity profiles and or lots of blue, which is 2 to 5 profiles versus the 21 to 50 profiles that Argo has achieved since this is done in the last 15 years. This is basically, in sort of the last 50 years of oceanography. An important point, again, is that Argo floats don't mind bad weather. So these are all the August temperature and salinity profiles from ships from 1951 to 2000. And these are 5 years of Argo profiles in the austral winter. So the floats are there all year long. Steve Briggs made a comment about this morning about what ships observe everything nowhere. And Argo is starting to make some stuff everywhere, okay? So I'm going to move on beyond Argo and really make the case that we can now do the same thing for biogeochemistry, ocean carbon cycling. And so the topics I'm going to touch on: why observe carbon, oxygen nitrate, biooptics in the ocean, the current status of sensor systems. I'm going to talk a fair bit about a basin scale experiment we're doing, a program called SOCOM, Southern Ocean Carbon and Climate Observations and Modeling, which is a prototype for a global Argo array, a BGC Argo array. I want to make the point all along that there's a strong linkage, not just to satellite observations in this, but to a variety of shipboard programs, the GoShip program, SOCAT program, and so on. And again, just talk about the path forward that we need to do to get to a global array. So why ocean carbon? Ocean carbon uptake is a major component of the global carbon cycle, the biological pump, the conversion of dissolved carbon dioxide to particulate organic carbon that then sinks from the surface ocean. Actually acts to lower atmospheric CO2 by about 100 parts per million. In the global anthropogenic carbon cycle, the ocean sink removes about 30% of the anthropogenic carbon, And if we really want to understand what happens on land in the global cycle, the net land sink is actually computed as the fossil fuels minus the atmospheric growth minus the ocean sink. So if we want to know what's going on land, we need to know what's going on in the ocean. And the final point is that interannual change is not well constrained in the ocean by observations. It's really constrained by models. Okay, so if we really want to have direct observational evidence for what's going on, we need more observations. A talk that was given at the Ocean Science meeting last week by Nikki Gruber toward a global synthesis of the ocean carbon sink since the mid-1990s. He makes the point that during the period 1994 to 2007, there appears to have been very anomalous weakening of carbon uptake in the Southern Ocean. So this is latitude 80 south up to 50 north. And this is either the anomalous flux of CO2 into the ocean or the anomalous storage of carbon in the ocean. He computes anomalous as the flux in this time period versus the flux in the time period before this up to the present, okay? And the point that he made at the end of this talk was, if this is correct, ocean carbon uptake is much more sensitive to climate variability than we thought, okay? That if there are strong changes in ocean uptake, maybe there can be things happen, good or bad. I also want to make the point that numerous studies point to climate and a decreasing ocean phytoplankton productivity links, papers like ocean primary production and climate, global decadal changes, climate-driven trends in contemporary ocean productivity, global phytoplankton decline over the past century. Corinne Le Carré gave a talk at the Ocean Science meeting last week, and again pointed out that we really don't know much about the biological pump in the ocean and how it might be changing in time. The satellites, these are all based on ocean color, primarily on ocean color observations. Same time, the authors of many of these studies have recently got another paper in Nature Climate reevaluating warming impacts on global phytoplankton, and they make the point that maybe the satellite ocean color signal is a reflection of physiological adaptation of phytoplankton to a warmer ocean rather than an actual change in the population. And my point here is that we need a better in situ observation system to really try and pin this kind of thing down. And so there's been a real paradigm shift in ocean observing. We now have a suite of autonomous biogeochemical sensors that are capable of being deployed for years, returning well-calibrated data over this time period. 15 years ago, no one could have given this talk, but in the time period in the 15 years, we now have a suite of sensors, oxygen sensors, phenomenally stable, optical nitrate sensors, pH sensors, and a variety of biooptical sensors for chlorophyll and particles. And these are all essential ocean variables, essential climate variables, okay? So oxygen. And again, I want to make the point that I'm going to talk about profiling floats, but these could be moorings, could be gliders, ship-based repeat hydrography, ship-based time series, ships of opportunity, volunteer observing ships. So all of these sensors, you can deploy them in a variety of different applications, but oxygen, nitrate, pH are all available to us now. Biooptical sensors for suspended particles, essentially optical backscatter sensors, chlorophyll sensors are all available, and these in particular have a strong synergism to ocean color remote sensing. So again, this synergism, the floats in ocean color, we can determine chlorophyll A, particle backscattering, depth of penetration of light, colored dissolved organic matter. And the benefits of this kind of approach are that, with the vertical profiling floats, we can see into the ocean, whereas the ocean color satellites see only about a fifth of the euphotic zone. Profiling floats operate under clouds in the Southern Ocean where there may be, no observations for many months at a time. And the combination of the two really become a much more synergistic product than one or the other. So Biogeochemical Argo has grown to be a global operation. This is a map from last September of the profiling Argo floats that have biogeochemical sensors on them now. Almost 300 with dissolved oxygen, over 100 with biooptics. There are probably, since September, quite a few have been deployed, probably close to 100 with nitrate and 50 or so in the ocean with pH on them. But there's no formal structure. And gosh, I think that many of the lectures we've heard this morning are that, you need to integrate, especially if you're doing climate. You need an integrated structure to make sure that your measurements are robust and calibrated and intercomparable and accessible and everything. So there has been a lot of planning on moving towards a more integrated system. The ocean OBS, adding oxygen to Argo, biooptical profiling floats report. The U.S. Ocean Carbon and Biogeochemistry Program had a scoping workshop on observing biogeochemical cycles at global scales with floats and gliders. Many more of these have taken place. And one of the themes through all of these planning documents that points to the next step is to do a regional basin scale experiment where we try and do the essential elements of what you would want in a global observing system, and really link this to data assimilating models as well to show the real synergisms of running a global system. And so I'm going to focus a bit now on the SOCOM project, Southern Ocean Carbon and Climate Observations and Modeling, again funded by the U.S. NSF polar programs with very significant contributions from NOAA and from NASA. So why the Southern Ocean? Well, it accounts for something like 60 to 90% of the excess heat in the ocean. In the Remick et al. Paper in Nature, almost all of the heat increase in the ocean is in the Southern Ocean. It accounts for up to half of the annual oceanic uptake of anthropogenic carbon dioxide, despite its much smaller area than half of the ocean. And turns out that vertical exchange in the Southern Ocean is responsible for supplying nutrients that fertilize about 3/4 of the productivity in the rest of the ocean. Paper by Jorge Sarmiento et al. So critical. It's also the least observed part of the ocean, and if we can do a prototype experiment in the Southern Ocean, we can do it anywhere. It's like New York. If you can make it in New York, you can make it anywhere, I guess, the way the song goes. So the goal of SOCOM is to put 200 profiling floats over 6 years with pH, nitrate, oxygen, and biooptics on them, with calibration tied to the GOSHIP program, the long lines of interior ocean observations. Link the data from the 200 floats to a Southern Ocean state estimate model to get the 4D fluxes of carbon and nutrients in the system. And finally, use all of this in an improved climate model and work with GFDL to predict the role of the Southern Ocean in future climate change. So all of these components are happening. The SOCOM program itself is led by Jorge Sarmiento at Princeton. I am the associate director of SOCOM, not the associate director of MBARI, of SOCOM. Okay. Theme 1, it's divided into 3 themes. Theme 1, observations, led by Lynn Talley at Scripps, Steve Reiser at UW. Theme 2, numerical modeling, led by Joellen Russell. There is a biooptical component led by Emmanuel Boss at the University of Maine. And Theme 3, education and outreach, is led by Heidi Cullen at Climate Central. It's a reasonably big program, 23 senior researchers at 11 different institutions. And beyond the support from NSF and so on, there's been just tremendous international support for this program. So we're deploying 200 floats. We essentially we're oceanographers with no ship time. Okay, we have floats, no way to get them in the ocean, and not much way to calibrate them. So we have a variety of international collaborators that have been making this happen for us. CSIRO in Australia, Tom Troll, a whole variety of people. Bernadette is here somewhere, raise her hand, has been very helpful. Avi in Germany has been very helpful, and I'll show you some data from floats deployed from a Polar Stern cruise. UK NERC crews, Yvonne Fearing was chief scientist. I've just deployed a bunch of our floats, and in general, the GoShip program has been very helpful. So to date, so the program's only been in the water for about a year and a half, okay? So we're just getting our feet under us. We have deployed 37 floats from March 2014 up to date. I guess we're getting close to 2 years now. I should change my scale. These are the floats we put into the Southern Ocean. We consider everything south of 30 part of our domain, but most of the floats, because we're funded by polar programs, get closer to Antarctica. We have 16 more floats on ships. Their float was just deployed last night, but the GoShip I-8 cruise going up right about here on Ravel is deploying floats right now. There will be an Australian P-15S cruise in just a little bit coming down here, deploying a bunch of floats, and then another Australian cruise in this region deploying floats. 37 more in construction for 2016. We're funded for 100 more over the next few years. And we're going to take the Southern Ocean from being the least observed ocean for carbon to being the most observed ocean for carbon. And see what happens with that data. So this particular slide sort of encapsulates what we're trying to do. This is pH measured on the U.S. GoShip P-16S cruise from about 67 south. Ship went up the line towards Tahiti, and they made all of these profiles. You see the dots for pH measurements. As they went along, they deployed 7 profiling floats. I'm just showing 3 of them here that have remained behind, and for now, almost 2 years, have collected pH data and taken the GoShip data, and now the data is all highly calibrated to the GoShip results, and taken this summertime snapshot of pH, and we can now extend these out into multi-year variability. So we're now getting the seasonal and interannual variability of pH in these regions, and trying to do this everywhere. If you're a ocean carbon chemist, you'll know that pH alone will not get you to carbon. You need one more parameter in the carbon system. And essentially, Brendan Carter, Nancy Williams, Allison Gray, Dick Feely are all part of the SOCOM program. And building on work that was done in Europe by Velo et al., have shown that we can estimate alkalinity as a function of salinity, temperature, and apparent oxygen utilization, and predict it globally with a set of algorithms. And this is the comparison between measured alkalinity and, they call it, I hate the acronym LIAR, locally interpolated alkalinity regression. But this is the comparison of the GoShip measured alkalinities and LIAR alkalinities. And so we're dependent on that to get to carbon. And if we do that, then we work everywhere in the Southern Ocean. So I'm going to show you an example of a float deployed from the Polar Stern last January, right here on the prime meridian. This is an ice-covered map in the summer. So ice probably was out to here in the winter. The float went in here and it popped up the day before Christmas right here. And we now have a full cycle of properties, this little square. So this is the year, January to January. I'm only showing you the upper 200 meters. This data goes on down close to 2,000 meters. The square is when there's ice. So we have last summer, the current summer coming into the system, temperature, chlorophyll growing in. So we see the ice edge bloom forming right here. Oxygen at the end of the summer, deep over winter, oxygen goes down, and the bloom happens. Oxygen is produced. Nitrate is drawn down each summer as the plants grow. pH, as the plants grow, consume carbon dioxide. The pH goes up, and so we have the bright red pH on each end. And if you use the estimated alkalinity, we can compute dissolved inorganic carbon drawdown each year, and the PCO2, the surface ocean PCO2, I'm showing here in the upper 30 meters, went high in winter under ice and then drawn down as the population goes on. And we're doing this now in 30 spots. There are 30 time series of carbon in the Southern Ocean, and the rest of the world ocean has a half a dozen. So we're rapidly moving towards our goal. This mixed layer PCO2 for the 7 floats that went in on the P16S line. This is a comparison of delta PCO2 in the ocean minus the estimated PCO2 in the atmosphere compared to the Takahashi climatology and the SOCAT V3 observation. So wherever there's an observation, there's a little gray bar over 50 years. Okay, so the observations are 50 years of data. Sometimes there is only one observation here for 9254, and we track the Takahashi climatology quite well, except climatology tends to suppress extremes, and we see a bit more extreme. When there's float data and a climatology has an observation, we tend to agree quite well, and the rest of the time, maybe the climatology is suppressing things. You can take this data and compute cumulative CO2 uptake. So this is, oh, by the way, I have to acknowledge Allison Gray, postdoc at Princeton, doing all this work, not me. The float would see the blue line for CO2 uptake over the year, and the Takahashi uptake would be the red line. Generally track each other pretty nicely, but again, I think that we actually have data in situ, and occasionally they diverge by quite a bit. These are both floats right at the ice edge or under ice, okay, and so you would expect the climatology to maybe be a little shaky in that area. So I'm going to switch out from SOCOM. This is work that Hervé Klauster is doing, making the point that chlorophyll A CDOM, this is a comparison of surface float data in black and MODIS satellite data in red for floats in the Mediterranean Sea, the North Atlantic, the North Pacific, the South Pacific. What I just showed in SOCOM we're doing for carbon, we can now do with float data properly calibrated and basically look at the satellite data seasonally under clouds when the satellite can't see, and we can see into the ocean interior now. So this is a subtropical, South Pacific gyre, the most optically clear water in the world. You get the vertical structure of chlorophyll A, and this would be the North Pacific gyre, another very low place. So we can really start to extend the satellite data in a way that hasn't been able to be done before into the vertical. So we get 4D observations of color and particles, and really, start to do just much more powerful. It's sort of the taking two different things and squaring the output. We have the power of force. So we have started regional programs. Hervé as well has a regional program in the North Atlantic and the Mediterranean doing incredible things. Planning for the global network has become. There was a meeting in Villefranche-sur-Mer. These were the attendees from 8 different nations that deploy Argo floats. A draft implementation plan is being written. One of the key points is how many floats do you need to do carbon in the world? And Joe Ellen Russell, Igor Kamenkovich, Matt Masloff, Allison Gray, again, have been doing a variety of OSCEs. This is one example. Take the CM 2.6 surface carbon flux. This is the 10th degree map, and randomly put floats into the ocean, resample it, and see how many floats you need to reconstruct the flux. And for many, and they're doing this for a variety of different things. The conclusion coming, so this is a reconstruction error now for 500 floats, for 1,000 floats, for 2,000 floats. They're finding that the changes for the things they look at are most pronounced between 500 and 1,000 floats. There's less benefit when you go to 2,000 floats, and so it's looking like an array of biogeochemical sensors at around 1,000 floats would get us, whoops, the daisy, I turned it off, get us close to what we need. So the conclusion of this meeting is that Biogeochemical Argo is an extension of Argo, and it really follows the main Argo philosophy. Our floats carry a suite of oxygen, pH, nitrate chemical sensors, chlorophyll fluorescence, optical backscatter, and an outcome of the Villefranche meeting was that we really should start equipping our floats with downwelling radiance. The floats, following the Argo philosophy, would profile to near 2,000 meters depth. The target array would be about 1,000 floats. All of the data is public in real time. It all would have to be quality controlled. And so this kind of encapsulates the bad news. With a 4-year lifetime, 250 floats a year would be required. That's $25 million a year. Floats are about $100,000 a piece. So, And really, Argo, by BGC Argo, should report to we should not be an independent program. We should work with Argo. So this is my last slide. I just want to make the point that BGC Argo really, its strength is its interaction with other programs. It needs GoShip for the calibrations, to resolve calibrations for deployments. As I showed with CO2, it would work great with the SOCAT kind of effort. It would extend CO2 into the intra-annual variation, and it has this obvious strong synergy with all kinds of satellite oceanography. It's something that we will see in our lifetime. Maybe not tomorrow, but it's coming. Thank you.